Any last questions? Hopefully y'all won't act too weird and just forget that it's there. Oh, and when I tell a joke, laugh really, really loud. Okay? So, okay. Alright, y'all have the paper out? Alright, so today, chapter 2.
Wait, what paper?
Paper for your notes.
Oh, okay.
We're going to be talking about how to graph position, velocity, and acceleration. And we've got 4 different situations that we're going to consider. 4 different scenarios. Scenario number 1. A ball that is thrown straight upward and then caught. We'll try to make it caught at the same level, something like that. What would the graph of its position look like? What would the graph of its velocity look like? What would the graph of its acceleration? So situation 1, ball tossed up and then it comes back down. In fact, that might be a good idea to draw a motion diagram. So it starts here, and when it's initially tossed, I'm going to draw the velocity vector. Okay, like that. But then what's going to happen to these velocity vectors as it goes higher and higher?
They get shorter
Yeah, they're getting shorter. Why are they getting shorter?
because they're slowing down.
Yeah, because the ball's slowing down. So again, we toss it up until it gets to the very top, in which case it'll be 0. It'll be stationary just for a moment. Got it. Very short. And then it's going to turn back around, okay? And its velocity vectors will look something kind of like this. Up and then down. Probably in your science class up to now, you've thought about maybe position graphs, or you've seen position graphs. You kind of deal with that a little bit in Algebra 1. Okay? But we're going to actually talk about the position graph, the velocity graph, and the acceleration graph. And we kind of previewed this the other day, and then we even saw it on Logger Pro. What did and I'll give you a second to copy that down. So the way that, before we talk about what the actual graphs look like, notice the independent variable on all 3 of these is t. So t is on the x-axis. The vertical axis is position, velocity, and acceleration. And you know what? I wonder, since this is moving up and down, is x the best variable for that position? No, what probably should I use instead?
Why?
Y. I agree with that. So y position. And in fact, this is the velocity, but I'm going to put the velocity and I'm going to put a little subscript y so we know it's the velocity in the y direction. We're just talking about one-dimensional motion. And just for consistency, I will say the acceleration in the y direction, since all of this is moving up and down. Alright, so does anybody remember what this graph looked like? Kind of make that motion with your hands. What did that graph look like? Yeah, it's sort of like that, doing the wave there. So if we released it at this height, then it went up over time, and then it started to go back down, and then we caught it again. So that, if we took individual time measurements, it would look like that. If we connected the dots with a smooth curve, it might look something like that. Now, let's think about the velocity of this ball, okay? As it's going up, how do you describe its velocity?
Positive.
Positive, okay? As it's coming down, how do you describe its velocity? Negative, okay? In fact, if we look at the length of these vectors, that kind of gives us an idea. You know, its velocity here, if we were to assign a number to it, what might be like, I don't know, 5. What would a number, like, we'll just say meters per second. What might be a number here?
4.
4 meters per second. Because it's shorter, and in fact, it's slowing down. What about here? 3. Here? 2. That worked out very nice for us. 1 and then 0 eventually, right? The velocity is 0 at the very top. Then we have, as it starts to go down, -1, and then -2, -3 meters per second. Would you all agree that it's negative? Because it's traveling in the, ooh, so much better than just saying down. Yes, in the negative direction, I like it. So something like that. If we were to plot these points, at time t equals 0, where am I going to plot this point? On the y-axis, but where? Down here, right here, up here? Near the top. Because at time 0, it's 5. Then, a little bit later, it's at 4 meters per second. See, this is like the 4. A little bit later, it's at 3, 2, 1. I'm going to try to make these graphs actually line up. At this point right up here at time, when it's at the very top, that's when the velocity is 0, right? So I'm going to try to get this. So that's when it's 0. So it's got to go 5, 4, 3, 2, 1, 0, and then -1, -2, -3, -4. That's a pretty weird graph, and you may have never seen a velocity graph like that. But Jesus, does that make sense? Velocity is 5, then 4, then 3, then 2, then 1, then 0 comes to a stop, but then it's -1, -2, -3, -4. You see how that's working out there? Okay? And then what about the acceleration? As it's going up, is it accelerating? Yes or no? Let's go. Yes. As it's going up, what is the direction of the acceleration? Yeah, it's negative. It's downward. Okay? So we've got negative acceleration all the way here. Okay? This is negative A. Pointing downward. What about after it reaches the top and it starts falling faster and faster? What's the direction of the acceleration? What do you think? As I let it go? Velocity, 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 velocity.
Positive?
No, it's not positive. It's negative. It's still, it's always negative acceleration. All the things, it's accelerating downward. In fact, at the very end of chapter 2, we'll find out that for an object in free fall, it is only being pulled on by gravity. It's accelerating straight downward at 9.8 meters per second squared. And that is, it's the same the whole time. Yes?
Is there ever like a situation where like say you toss another ball or in any other sort of situation where the acceleration does change?
We'll find out in like chapter 4, I guess. The only time that ever you have acceleration, there has to be a force. There has to be something pushing or pulling on it for there to be acceleration. And if I let this ball go, there's only one thing acting on it, and that's gravity due to planet Earth. If I throw it up, as soon as it leaves my hand, there's only one thing acting on it. Gravity the whole time. You say, what about the air resistance? If Mission was here, he would say, what about the air resistance? And I'd say, yes, but the air resistance is so ridiculously small in this case that we just kind of ignore it. Okay, we say it's negligible.
So
Eventually it's not, but yes.
does it ever, so there can be instances where the acceleration does change?
If there would be of a ball that's thrown up and down, then it would basically, it would have to be
Change
due
in
to,
force?
it would only be due to the air. That's the only thing that would be acting on it. Unless, you swing a racket, or your hand, or, a bat, Other than that, the acceleration is always going to be downward, and it's actually always the same number. This is a little bit advanced for us right now, but that's okay. It's always this right here. It's always actually negative 9.8 meters per second squared. What in the world? We haven't talked about acceleration a whole lot. What is this? Well, just take my word for it. Object traveling up, down, always accelerating downward. It's the only thing that's acting on.
Is it like everything, does everything always go down at that same speed
Area
in
underneath.
free falling?
At that same acceleration? Yes.
Not the grass.
Everything does. Why? We don't want to get ahead of ourselves. Okay, so those are the three graphs, okay? You need to pay attention to what is on the vertical axis to be able to understand what's going on, okay? Anybody have another question on this? Okay. Consider situation number 2. And that is a car driving down the road at a constant speed, slows to a stop, then speeds up. So we'll say car stops at stop sign, then it speeds up. And just like we did over here, let's do a motion diagram of this. So first off, the car's traveling along at constant velocity, so I'm going to do maybe 2 or 3 of these at about the same length. So constant velocity. Then it's going to start to slow down for the stop sign. So I'll make these a little bit shorter. Comes to a complete stop. Then speeds back up again. And then finally, once it reaches the cruising speed, it stays at that cruising speed. Just to be clear, we've got constant velocity there. We've got constant velocity at that point. Like, that's when this is when you hit the cruise control, button on, and you're going 65 miles an hour, 55 miles an hour, whatever it happens to be. Alright, so that's our situation. We're going to now draw our 3 graphs. Now we're dealing with something horizontal, so should I use X or Y for this vertical? Yeah, we're going to use X because this is the position, and it's something that's moving just horizontally. So X, velocity in the X direction, and acceleration in the X direction. Time, time, time. Always time on the horizontal axis. Now we have to decide where do we want our origin to be in this situation. We can put it in the middle, we can put it at the end, we can put it over there. For our purposes, I'm just going to set this right here as our origin, and everything obviously over this direction is positive. So at time t equals 0, the car is right there. That would correspond to 0 on the X position. As time goes on, he's traveling at a constant velocity. That is represented by a straight line. And then he starts to slow down. So if he starts to slow down, that is it's gonna be kind of curvy. It's gonna be something kind of like this, until it comes to a complete stop right there. Maybe just for a second. Then he's going to start to speed up. We'll find out later that speeding up and slowing down are curves on this position. And then he's going at a constant speed, and so that's gonna be yet another straight line. So here is where he is speeding up. Here's where he's slowing down. And then right here, this is where he has the constant velocity. Can y'all see that okay? Anybody have a question on that? Okay. Let's go over here and assign some numbers to our motion diagram. How fast do we want to be going right here? 30 miles an hour. 30 miles per hour. 30 miles per hour. Okay? Then we're going to slow down, and eventually we're going to be at 0. Okay? So 30, 20, 10, 5. Then speeds up, 5, 10, 20, and speeds back up again to 30 miles an hour. So our velocity graph, what am I going to do first? Start at 30. And then what? Straight line? Which way? Up, down, or horizontal? Horizontal to the right. Okay. Then, if I can, I'm going to try to get it so that it just lines up. That point right there. So that's where you've got the constant velocity. Then as he's slowing down, eventually I'm going to slow down to 0 at this point right here. These dashed lines are kind of helping line it up. So it's going to be straight like that, slowing down, going to a 0 velocity. Does the velocity go negative?
No.
Why not?
It doesn't go reverse.
Doesn't go in reverse. It's always traveling constantly in the positive direction. So it's going to hit 0, but then as we speed back up, we're at 5, 10, 20. Speeding back up, and then constant velocity, 30, 30, 30. Something kind of like that. Have you all ever dealt with like velocity graphs like this, or is this kind of a new thing? Kind of a new thing? Alright. Let's talk acceleration over here. Anton, what do you think? Acceleration during this part right here. Negative, okay. Anybody agree or disagree? Or positive?
There's no acceleration.
He says no acceleration. Well, acceleration, if you remember, we gave the definition the other day, is how much the velocity is changing. Anton, do you want to change your mind? Positive, negative, or 0?
I'm going to say negative.
Alright? Answer in fact is 0.
0.
Okay? Because there's no change in the velocity. Okay? So, 0 acceleration during this entire time. So, Anton, maybe another shot here. What about in this region where he has 20 velocity, then 10, then 5?
I get it now. Okay, it's negative there.
Okay, totally agree with you on that. Okay? Acceleration in that direction, which happens to be negative. And then what about this region? Somebody else? After he stops, now he's accelerating positive during that period, and then at this point again, 0. So, acceleration is 0 for that first bit. Then it becomes negative for this region right here. Then as he's speeding up, his acceleration is positive. And then once he's going at a constant velocity again, it's 0. So the graph kind of looks something, might be like, some poles and circles, but we'll just, just sort of a rough idea about what's going on. I've purposely picked these situations, okay, because it sort of involves all the different types of interactions that you could have. Something speeding up and slowing down, same thing with the ball. And hopefully next week, we are going to do a lab where we do some video analysis of these very same scenarios. Okay? Scenario number 3. This is where a ball is rolling to the right, hits a wall, and then bounces back, rolling to the left. Scenario number 3. Ball rolls to the right, hits wall, bounces, I don't want to say bounces, maybe we can say rebounds, or whatever. I don't want to say bounces because that may have vertical motion. So it rebounds and rolls to the left. So our motion diagram looks something like this. Rolling, rolling, rolling. Hits the wall almost instantaneously. It is now rolling, rolling, rolling. That way. We have our 3 graphs. Time on all of them. I'm going to use X for position because we're talking about something that's moving horizontally. I'm going to say velocity in the X and acceleration in the X. We're going to try to start speeding this up so we kind of have this totally under control now. We need to define our origin. And I think in this example, once again, I chose the starting as where it's rolling from as the origin. We could make the middle of this ball's motion the origin, or we could make the wall the origin. It really doesn't matter, but I'm gonna put it right there so that at time 0. Actually, let me take that back. I'm looking now at more detailed on my notes. I have made the origin the wall. Or no, did I not do that? Hold on. Okay. That's where we're going to make the origin. There we go. So, its initial starting position is somewhere over here in negative territory. So, where am I going to put my first dot? Up here, down here, in the middle? Where am I going to put my first? Below, right. At some point, it's going to pass through the origin. When it passes through here. Then it's going to hit the wall at this time, and then its position is going to pass back through 0 and start being negative. So, right here is where it hits the wall. Let's throw some numbers up here for the velocity. What would be some numbers that we could have here for this velocity?
3, 2, 1.
Okay. You might think so, but we're going to have this ball it's rolling at a constant velocity. 3 meters per second, 3 meters per second, 3 meters per second. We're going to just assume that this ball, when it hits the wall, instantaneously it starts bouncing back. Now, if we had a high-speed camera that could take like 400 or 500 frames per second, we would actually see it squish, all right? And then we'd see it unsquish, and then kind of go back. And we are going to talk about that and what all those interactions that are going on, but that's not like chapter 9 and 10. Okay, so we'll see that happen. The same thing happens when you kick a football. Oh well, y'all don't know what football is. When you kick a soccer ball, okay, or when you hit a volleyball, it actually squishes and then it bounces off. I'll give you some extra credit if you end up take a high-speed video of you doing that. 2, 1. No, same length.
Negative.
-3, that's right. See? It's traveling to the left. -3, -3, -3 meters per second. Okay. So 3, 3, 3, 3, 3 up until it hits the wall. Then -3, -3, -3 after it hits the wall. Does that make sense? Okay. Next up. Acceleration. What do y'all think is the acceleration as it's rolling to the right here?
The same.
What do you mean by the same? Hold off that thoughts.
Going positive, but at a constant rate.
Right, so because it's going at a constant rate, is there any acceleration? No. Acceleration is when those velocity vectors are getting longer or getting shorter. So if it's going at constant velocity, the acceleration is 0. What about when it's going this way?
Still the same.
Yeah, it's still 0. 0 acceleration the entire time. Now, this is assuming an instantaneous point of contact. There is a very quick moment when it spikes and does this weird thing right here, but we're going to ignore that for right now. There's 0 acceleration altogether. Okay? Last situation. Situation number 4. Ball is going to roll up a hill, stop, slow down to a stop because it's rolling uphill, then start rolling back down a hill. Maybe you're driving your car, you're driving up a hill, and then all of a sudden you run out of gas, and you put it in neutral. You just coast up, but then you forgot that you put it in neutral, so your car starts rolling back down. That would be dangerous. So situation number 4. Here's our number line. I have decided, I'll tell you this from the very beginning the correct way. We're going to actually make our number line tilted to match the motion. And we can have our number line be horizontal, we can have it be vertical, we can have our number line horizontal. Or sorry, no, diagonal, rather. So here comes the ball or the car or the boulder. It's traveling along, but it is slowing down. Eventually it comes to a stop, just for a moment, and I should write these arrows on top of these other ones. It's going to come right down, but for the sake of us being able to see what's going on, then it's going to start speeding up as it rolls back down, which is an interesting phenomenon. That actually, when it passes by this spot again, the value of its velocity is the exact same, but it's just in the opposite direction. So if it's going like 10 miles per hour up this way, slows down, comes to a stop, and as it comes back down, that's going to be going 10 miles an hour, but the opposite direction. Same thing happens with a ball. If you throw it up or shoot a gun, shoot a bullet straight up, and it's traveling like 300 meters per second, muzzle velocity whenever it leaves, okay? And it goes up, you're like, it's not going to hurt anybody, it's just going to go up and come back down, okay? Well, it has all that time to slow down, and then it's going to start accelerating as it comes right back down. But when it comes straight back down, it is as if, if I have the gun right here and shoot it, the bullet has the exact same velocity at that same level, but now in the downward direction. So it would be just as deadly as if I just took the gun and pulled the trigger right there. So you see, like, these people, like, 4th of July and stuff like that, or not 4th of July, maybe whatever, some celebration, New Year's or whatever, they're shooting the gun in the air, like, ha ha ha, and they're like, somebody somewhere better watch out, because that bullet's going to come down with the exact same velocity. Alright? So, We've got our three graphs. Should we call this X or Y or something else? It really doesn't matter. We'll call it X. X-axis. We'll call that being the X-axis, and the acceleration, the X-axis. Time, time, time. And for the sake of time, I'll just show you right here. We're going to start off, if you notice, our starting position is a little bit in the negative direction. So we're going to start down over here, and it's moving more and more positive. We'll find out later this actually turns to be, it's kind of like it's a quadratic, it's sort of like an upside down parabola. If we were to continue it out, it would look like this, like a quadratic. But the thing is that it stops at one point, alright? Then, actually I take that back, it is going to be a full parabola, because then it's going to start going back down this way. Let's assign some numbers to reality here. 10, 8, 6, 4, 2, 1, 0. It's all positive as we start going down the ramp. All negative. Negative 1, negative 2, negative 4, negative 6, negative 8, negative 10. So velocity starts off over here. This point right here, this is the point where it turns around, okay? This is the turnaround time. And we notice that at the turnaround time, the velocity is 0, so it's going to look something like that. It turns out that it's linear. And then after that, it becomes, negative 1, negative 2, negative 4, negative 6, negative 8. So, to use that same slope, we're trying to make that same line. All right, almost finished. What is the acceleration, positive, negative, or 0 as it's going up the hill?
Negative acceleration,
Why do you say negative?
because it's slowing down.
Okay, but you remember, negative acceleration does not mean slowing down. It's
Because of velocity.
the velocity is what? Velocity is decreasing, okay? So its acceleration is in the negative direction as it's going up here. Totally agree. Right to there. What about in this part right here? Somebody else? You say negative? I say negative as well. Look, it's accelerating in the negative direction.
Oh, got you. Okay.
So, same. Okay? So, today we talked about 3 different types of graphs. What were they, class? Velocity, acceleration, and position. I would have put them in that order, but that's fine. Y'all are plenty good. If you draw the motion diagram, okay, and make sure you have your origin, then and start assigning some numbers there, that makes it a lot easier to graph. When we come back on Tuesday, I'm going to give you some situations. You're going to have to identify the graph. Or I may give you the graph, and I'll say, hey, what's going on? Is this thing speeding up? Is it slowing down? What's going on with all that? And then a little bit later on next week, we're going to start dealing with formulas and the formulas that govern all of this. We're going to find out that, hey, there's some actual relationships between those graphs, and you can, if I just have this graph, I can make this graph. Or if I just have this graph, I can write that one. And then hopefully we'll be doing those experiments, those scenarios, 3 or 4 of those actual things, and we will be analyzing those with the computer and having the computer draw the graphs, which will be super cool. All right? Thank you all for watching. Hope you got everything.
You have a light to spread.